Thank you very much. Thank you for the introduction and for the invitation. I've never been here. It's my pleasure to be here for the first time. I'm going to talk about a little bit about my research concerning the interplay between quantum theory and black holes. In particular, there is this research field called relativistic quantum information, and that essentially concerns what people normally do in quantum information. They analyze quantum information as a resource. They use it for different purposes, for communication, for teleportation, for computation, and the typical assumption in all these schemes that are considered is that everything happens in a fixed inertial frame of reference. There is no motion involved. There are two parties that communicate, for example. They want to teleport a quantum state, and both of these parties are at rest. They do not move. And the idea is that motion is not really relevant because it does not change much in these protocols. And in fact, to a good approximation, this is true. To a good approximation, you can neglect all the effects of motion, in particular the fact that we are sitting in a gravitational field, because gravitational field is weak and does not affect in a serious way what happens if you communicate using quantum states. However, in principle, it turns out that the role of gravity is very important and can be very important if gravitational fields become really strong. Obviously, it does not concern us here, but in principle, if you plan to communicate over large scales in the future, for example, across the scales of the solar system, even further away, then we will probably at some point need to take into account relativistic corrections to all these protocols. And what I've been doing for a couple of years is researching this question: what happens if you take gravity or non-inertial aspect of your motion seriously? What really happens? And this is really theoretical work. It does not translate directly to any observable consequences right now, but possibly in the future. And another aspect of this is that we are still searching for the quantum theory of gravity. It has been 100 years, we haven't found one yet, and what this research can somehow help understanding what are the requirements for quantum theory of gravity in some limited cases when we are not sitting in the quantum gravity scales of energies, but we are in the semi-classical limit where accelerations of gravity is really strong, but we are not yet in the regime of quantum gravity. And somehow the asymptotic properties of the theory could be revealed in questions that I will be discussing today. So the whole story starts with this nice blackboard. Not sure if you are familiar with it. This is the blackboard that was placed in Richard Feynman's office when he passed away. In fact, he left for a surgery and he never went back. He never came back. He died during that surgery, and he left this set of notes on his blackboard, and somebody took a photo. And there are some interesting remarks here. For example, he said that he wants to know how to solve every problem that has been solved. Very ambitious goal. But there is also a section of small problems to learn in the right-hand side. And among these problems, there is one that is particularly interesting. It's I circled it here. It says accelerated temperature, and this little note refers to something that we nowadays call the Unruh effect. And there is this effect that Feynman wanted to learn about, and he never had a chance because he died too soon. And in fact, I had a chance to talk to Unruh. We went to a conference together, and then we are going to we shared a cab on the way back to the airport, and we had a conversation. I asked him about this, whether he knew that Feynman wanted to learn about his effect that he discovered in the 70s and never had a chance. And Unruh, who is a kind of big guy, like a Santa Claus looking bit, he replied in his style that, well, I once tried to explain it to Feynman, but clearly he did not understand. So there you go. The first thing I want to talk about is this Unruh effect, because it's going to be crucial for the understanding of this whole field I'm going to discuss. So, imagine you want to measure a beam of light. For example, you have a single photon that you produce, and the photon is characterized by a certain frequency, say it's green, and you want to measure that photon. Then the first problem that appears is that the color of the photon is going to crucially depend on the observer, because we have the Doppler effect. One observer can say that the photon is green if he or she makes a measurement, but then another observer that is moving with constant velocity will see that the photon is not green but red. And that's because the frequency shifts when you move. It's like a standard Doppler effect. So there is a relative concept here that the property of the photon can change from the observer to the observer. This is not nothing very spectacular. This is a known fact even for classical light. And what happens here is that there are some things that change and there are some things that do not change. What changes is some properties of the photon, the color, maybe the direction of propagation, but the number of photons is the same. Both observers would agree that there is a single photon. And this, what I just said, is only true in a special case when the observers are inertial. Because when they accelerate, when one of these observers accelerates, then not only that they do not agree on the color of the photon, but they also do not agree on the number of photons. And the extreme case of this has been discovered by Bill Unruh around 74, I guess, 75. And that's what we nowadays call the Euler effect, is the situation where the first observer sits in the vacuum, in the quantum vacuum. This is the most empty state, I mean, as empty state as you can think of in quantum field theory. So it's not that there is nothing, it's the vacuum state. It has some properties. And an interesting property of that state is that when you accelerate through the vacuum, you do see particles around you. And the number of these particles depends on your acceleration. The more you accelerate, the more particles you see around. And to be more concrete, it turns out that the state of particles that you see around you has properties of a thermal state. So it's the same state that you see coming from an electric source of light, a bulb, for example, that emits light at a certain temperature. That temperature of particles around you is proportional to acceleration. Which is crazy, because in principle, it turns out that not only the properties of your particles are frame-dependent, observer-dependent, but also the very existence of these particles is frame-dependent. So not only that these particles that we are built of are strange, they behave according to quantum theory, but also we cannot even say that they exist in absolute sense. The existence of a particle is a relative object, a relative property. So this was a discovery made in the 70s. Not strange that Feynman was surprised by it, because it's very unintuitive, but it turns out that this is just a consequence of relativistic quantum field theory. And the effect is very, very weak. The number of these particles in the vacuum is proportional to acceleration, but the coefficient of proportionality is very, very small. It's roughly 10 to minus 19, I guess. So in order to see 1 Kelvin of a temperature, you would need to accelerate with accelerations of the order of 10 to 19 G, which is practically impossible. However, in principle, that effect is there, and it's crucial. It has not been yet observed experimentally. I'll maybe mention that later on, if there is a chance to observe it experimentally, because there is a chance to observe it, but it's not so straightforward. But in principle, that effect changes our idea of quantum states. And I gave an example of the vacuum state. The vacuum state turns out to be frame-dependent. One observer says it has 0 particles, the other observer will say there's a lot of particles. And first consequence of that is that not only acceleration will have this property of affecting number of particles, but so will gravity. Because in general relativity, the idea of gravity is that it should be equivalent to some degree to acceleration. For example, this room here has no windows, and according to principle of equivalence, we cannot determine whether we are sitting right now in a fixed gravitational field, or there is no gravitational field at all, but the whole room accelerates up at a certain rate. These situations are locally indistinguishable. Therefore, we should expect that the gravity will have a power of changing the number of particles even if it's a classical theory. Not to mention the quantum theory of gravity that we don't know. But so here's this first interesting observation, that gravity can affect quantum states. And that concerns not only the vacuum state, this is just a special case, but any quantum state I can think of, any number of particles I have, that number of particles and the properties of that state will depend crucially on the question who is the observer. So this is a relative notion. Now this effect is very closely related to the so-called Hawking radiation that you probably have heard of, it's more popular. Hawking radiation takes place when a dust of matter collapses and forms a black hole. If there is a very diluted gas that eventually collapses gravitationally and forms a black hole, then at the initial state of this process, there is almost no gravitational field because the gas is diluted and it does not forms any strong gravitational field. But as it collapses and forms a compact object, then that compact object around it will create a very strong gravitational field. In particular, if that's a black hole, that field can be really extreme. And an observer that is sitting nearby will observe that the gravity around him is increasing. So in the asymptotic past, very long ago, there was no gravitational field. Long in the future, there will be very strong gravitational field. So that situation corresponds to changing a frame of reference from one in which there is no gravity to one that has strong gravity. And since I already explained that due to Unruh effect, you should expect that changing a frame of reference like this will result in production of particles in the vacuum. And for the same reason, when you are sitting next to a black hole that increases its gravitational field, gradually you will eventually see a stream of particles coming out. And that is called the Hawking radiation. So no strange that these two effects, Hawking effect and the Unruh effect, have been discovered practically at the same time. 1 year difference between these two papers. So that's what I mean, roughly speaking, this is what I finally wanted to understand. Now, the question about what are the consequences of that fact to the theory of quantum information. I said before that people consider stuff like teleportation or computation, dense coding. There are many protocols where you use quantum states to communicate, to compute, and essentially, if you take into account the gravity side of things, then the natural consequence should be that all these protocols, the fidelity of teleportation, the fidelity of computation will depend on the context. It will depend on where is your computer, where is your teleporting device. If it's located close to the black hole, for example, which is a crazy science fiction scenario, but we can just consider it theoretically, then that device will be affected by the presence of gravity. And what we are doing is that we just essentially wrote a bunch of papers asking this question: what happens if you try to perform some sort of quantum task using quantum information protocols, but one or two of the observers are affected by gravitational fields? And for example, in order to perform quantum teleportation, this is a very basic, one of the most basic protocols in quantum information theory. Essentially, what happens is that you have two parties. You have Alice and Bob, or two observers, and one of them has some quantum state, and that state is supposed to be sent to the other observer, but you cannot send it directly. There is a barrier between you. You cannot just send it physically. You have to use some other protocol. And that other protocol that works is called teleportation, and teleportation works in the following way. These two observers must first share an entangled state of two particles, and then on top of that there is an extra quantum state that is in possession of one of the observers, and the protocol goes like this. You use this entanglement that you produced at the beginning, you apply some operation on one side of the protocol. One of the observers performs certain operation, destroys your entanglement, but after the measurement can send classical information to the other party, and that is enough to recreate the unknown quantum state on the other side. And the magic of this protocol is that you do not have to send anything directly other than sending classical information, that's calling, making a phone call, which contains no information about the state you want to teleport, these are some details that I don't want to go into because this is not object of this talk. However, the crucial point here is that in order to teleport a quantum state, you first have to have an entangled state between two parties. And the question is here, what happens to entanglement if gravity is involved? For example, I could produce an entangled state of 2 degrees of freedom, 2 wave packets, and I would like to use this entanglement to teleportation. In the ideal case, if nothing happens to entanglement, I could teleport a quantum state. But then suppose that one of the guys who is holding one of the part of the quantum state happens to fall into a black hole, or be close to a black hole, or is in the presence of some strong gravitational field, or, to make it more simple, starts to accelerate. Because it's the same. I mean, according to classical theory of gravity, there is no difference whether you're accelerating or you're sitting next to a strong gravitational field. So suppose that one of these guys is accelerating. How does this acceleration affect the amount of entanglement that they possess? So one of the projects that we've done is looking at this question, and this is one of the possible outcomes. It turns out that if you look at how much entanglement you have, that's the vertical axis, amount of entanglement, and on the horizontal axis you have amount of acceleration that you undergo, then it turns out that as you accelerate more and more, the amount of entanglement that you share with the other party decreases. So gravity or acceleration has the kind of negative impact on the amount of entanglement. It destroys the entanglement in a way, or it makes the whole protocol more complicated. I'm a bit oversimplifying this, but the general rule is that the presence of all these non-inertial effects, gravity and stuff, will affect in a negative way your ability to communicate. Therefore, if there is somebody next to a black hole and wants to teleport out some quantum state, it will be more difficult due to gravity. And the closer to the event horizon you are, the more difficult it is going to be to communicate. And I'm not going to talk about crossing the event horizon. I'm still sitting on one side of the event horizon, from which classically you could just escape, and yet it still affects your ability to communicate in a negative way. This is the amount of entanglement that is dependent somehow on acceleration. We have considered different technical, different initial entangled states, so there are a few curves here, but all of them will have this characteristic of being degraded as you increase acceleration. And if you put it in the context of teleportation, this translates in the following way. If your entangled state is imperfect, if it's affected by these gravitational aspects, then the state that you try to teleport turns out to be distorted. So in the ideal case, after teleportation you had a state here, and then it ends up on the other end of the room. If the entanglement is degraded, then the state that you recreate, that you teleport on the other side, is not perfectly the same state. It changes. And there is a measure of that, how much the state changes when you teleport imperfectly. That measure is called fidelity of teleportation. And here there is a plot of this fidelity, which is perfect, is equal to 1 when the color is yellow or white, and it's degraded when it's going to be red. And there are different cases, different scenarios when you try to perform teleportation, and the two parties involved start to accelerate or are experiencing some gravitational field. And on the horizontal axis, there is gravitational field on one hand side of the protocol. Here, there is acceleration of gravity on the other side of the protocol, and you see that as you increase acceleration by any of the observers, the amount of the fidelity of teleportation drops. So you see that it's kind of symmetric, so that if one of the parties accelerates, there is less and less fidelity of the teleportation, and eventually, when you reach the red region, when the fidelity is equal to 1/2, this is essentially sending a noise. It's too noisy to be even called communication. So the general rule here is that this interesting Unruh effect can translate into practical problems with doing any sort of quantum information protocols. And that applies to all sorts of stuff. Obviously, again, let me stress this. In normal gravitational fields that we are sitting in, this effect is very, very weak. So it can be safely neglected. But in principle, as we increase the scales of communication, these weak effects can start to play some role in the future. Exactly the same way as classical gravity plays a role in GPS communication. As you probably know, the GPS system has to use corrections from general relativity, otherwise it would fail to be precise. And so far the communication is purely classical, there are no quantum effects involved. However, there are already first experiments communicating with satellites using quantum states. There was this famous Chinese experiment where they shared an entangled state with the satellite, and that was already a communication protocol on the scales of hundreds of kilometers. And eventually, you will increase these scales, and eventually these relativistic corrections to these protocols may start to be relevant. So maybe this is the song of the future, but well, for now we don't have to worry. That's definitely not a problem right now. But theoretically speaking, this could be interesting.
Can I interrupt?
Sure.
With my clarifying question. So you have two particles, and you know that they have opposite spins, yeah, they are entangled, and then you start accelerating one of the particles, and then what you are saying is that the probability that they have the opposite spins is decreasing, right?
Yes.
This is what you are saying.
Yes.
Yeah? Okay.
I mean, in this particular protocol, we are using different type of entanglement, because spin is one possible degree of freedom. In these protocols, we are using a different type of entanglement, where not the spins are entangled, but the number of particles are entangled. So it's a slightly different protocol, but in principle, the same thing would translate to spins. In fact, for the spin entanglement, there is already a problem when you talk about inertial motions, because when there is a spin entanglement, 2.5 particles are entangled in a usual way. When one of the observers moves with a constant velocity, then it turns out that the velocity, constant velocity, affects the direction of the spin. And the spins are kind of shifted or tilted when you move with a constant velocity. You don't have to accelerate for spins. And that makes the spin entanglement decrease. So that would be also the effect that, I am not discussing this, but that would be another effect. And you could ask what happens to the entanglement when you move. Why does it decrease? Well, it turns out that there is the spin entanglement is degraded, but there is an extra degree of freedom in motion, and it turns out that the motion is entangled with the spin. And so the whole state becomes very complicated. It becomes a complicated, multi-dimensional entangled state that when you only restrict yourself to looking at the spin entanglement, effectively it's decreasing the entanglement. So also kinematical effects for spins, even with regular constant velocities, can play a role in communication protocols. What I'm discussing is slightly different, but this also shows that you have to be really careful when you're taking into account relativistic corrections to all these protocols. So that's why it's really safe and easy to consider quantum information, assuming that everything happens in a fixed inertial frame of reference. And as you try to include relativistic corrections, things become much more complicated and you have to be much more careful, and sometimes it's even very difficult to formulate a problem. For example, this calculation, I mean, this solution to this problem took us roughly 10 years, the whole community, and there was many mistakes, many errors in literature, and I think we were the group that I was leading for a couple of years eventually found a solution that was free of any problems. But this was a really tricky question. I think at some point there was something of the order of 200 papers about this that were wrong.
So this is entanglement between number of particles?
Yes. For example, I could have a state where there is 0 particles, or you have 1 particle and I have 1 particle, or you have 2 particles and I have 2 particles, and all these scenarios are superposed. So there's quantum superposition.
Like a particle and antiparticle scenario?
No, not really. So entanglement is a property of 2 degrees of freedom. You can entangle any degrees of freedom you want. for example, we were talking about spin entanglement. You can entangle a spin of one particle with spin of another particle. You could entangle colors. You'd have two photons that are entangled with frequencies. So this photon is red and this is yellow, or the vice versa. So you could entangle other degrees of freedom, but you could also entangle number of particles. This is other type of entanglement. And in principle, you can entangle any property of physical property you want. You can entangle momenta, positions, spins, colors, number of particles. Anything that you could measure could be entangled. So this is already the situation in quantum field theory, where anything in principle could be entangled, and usually is. The question is how to create that entanglement in a way that you can control it and use it for something useful.
But how many bits of information you should send to recount the second stage?
Yes, very good question. So this is extensively studied in regular non-relativistic quantum information. The amount of entanglement you have to use as a resource depends on the size of the state you want to teleport. For example, if you want to teleport the smallest state possible, like a single spin on half, that takes a single entangled state of two spins. But if you wanted to teleport something bigger, that has a larger kind of space of larger Hilbert space, you would need more entanglement. You have to entangle objects that have more degrees of freedom. And that's essentially translates directly into... So, amount of entanglement you have to use depends on the size of the state you want to teleport. Essentially that. And there is this particular type of entanglement we are discussing here. These are some technical details I normally don't go into, but since you're asking. So, these particular entanglement state that we are using allow you to teleport any state you want, any size of the state you want, because you can just crank up this entanglement without any limits. So these particular states we are considering are called two-mode squeezed states in quantum optics, and the amount of entanglement in the two-mode squeezed state can range from 0 to infinity. And you can pick any entanglement amount you want, and that will allow you to teleport a certain amount of information. Any other questions or comments? So the purpose of this talk is to give you a kind of review of questions that we are asking. I'm not going to go into details unless you ask, then I'm happy to go into some details, but I will just give you a landscape of questions that can be asked within this interesting kind of relativistic version of quantum information theory. Okay, so this is another paper that we wrote that is somehow related to the Unruh effect. And this reveals another paradoxical property of quantum theory. You probably know many of them. You know that in quantum theory particles behave in an unpredictable way. They can be in quantum superpositions, which means that they behave as if they were at several places at the same time. Now you have learned that these particles can appear or disappear depending on who is the observer, so they behave in a very non-classical way. And here there is a very interesting observation that we have made concerning the emptiness, the quantum vacuum state. And the particular question we are asking is this. Suppose that you have an empty cavity. Cavity is essentially two mirrors. So there are two mirrors, they define boundary conditions in space, and suppose that the space between these mirrors is empty. So there is a vacuum state of all the modes inside of the cavity. It turns out that when you change these boundary conditions by introducing an extra mirror in the middle, so suppose that you slice the cavity in half using an extra mirror, and that mirror separates modes from on the left-hand side from the ones on the right-hand side, it turns out that introduction of the mirror will show that there are some particles produced by this process. And effectively, it will look as if that extra mirror produced particles on both sides of the cavity. Not only that, it turns out that these two particles on left-hand side and right-hand side, these groups of particles, will be entangled between each other, there will be some entanglement that they share among themselves. In principle, that entanglement could be useful for example, for teleportation, but in principle, there is some entanglement created by interaction of the mirror. Now, you could say that entanglement has been created by introducing the mirror. But this is not entirely true. And in order to reveal that, we have made a very interesting calculation. We have introduced not one mirror in between, but two different mirrors at two different points. And each of these mirrors will dissect the cavity into parts, and with two extra mirrors we'll have three parts of the mirror, of the cavity. And each of these extra mirrors will produce some particles that there will be entanglement between them. And the interesting part is that not only the particles on both sides of each mirror will be entangled, but also the particles on the most on the left hand side will be entangled with the particles most on the right hand side. So these two different mirrors will produce particles, and these groups of particles will be entangled between each other. Which is crazy, because you cannot create entanglement at the distance. If you want to create entanglement of two particles, you have to bring them together, make some operation, and then they become entangled. There is a theorem in quantum information that you cannot create entanglement by creating two actions at two different points, for example here and here. By doing something locally here and doing something locally here, I'm not able to produce any entanglement. It's a mathematical theorem in quantum information theory. And yet it seems that we do that in this problem, because we introduce two different mirrors at different points, and they produce particles that are entangled. And we can verify, we can compute that entanglement, turns out to be non-zero. How is it possible? Well, it turns out that you cannot create entanglement, but you can reveal entanglement that was present in your system from the very beginning. And the interpretation of this calculation is that the vacuum states that we have started with already carries some sort of entanglement that is hidden in the degrees of freedom that you cannot observe directly. And the interpretation of this crazy calculation is that you do not produce particles by introducing a mirror. You do not produce entanglement by introducing a mirror. You reveal that entanglement, and you reveal these particles by changing the bipartition of the state, by changing the degrees of freedom that you have access to. So it turns out again that the vacuum state is a very complicated object. It's not that it's just nothingness, but this nothingness has a very interesting and intriguing and complicated structure that can be revealed by changing the way you observe the vacuum. For example, if you accelerate through the vacuum, you find particles around you. You don't create these particles, they are there, it's just you have changed the way you observe the vacuum state. And another side of this experiment is that, of this consideration is that it turns out that if you observe an Uller effect with one detector that accelerates to the right, and there's another detector that accelerates to the left in the opposite direction, and both of them see some particles in the vacuum, it turns out that the particles that these guys see are entangled. Again.
Can you explain us, okay, well, you're accelerating the vacuum and you see the particles, so you are seeing anything else than like particles that appear due to appearance of particle, antiparticle, and when you are not accelerating, you see these pairs, particle and antiparticle, in a different way than when you are accelerating, or there is something in addition to this, yeah?
It is very tempting to have this analogy. In fact, even Hawking used that analogy when he was talking about Hawking radiation. He said that you have this radiation because there are pairs of particles produced on the event horizon, and one goes inside, one goes outside, and these outside you can witness, and you call that Hawking radiation. In fact, I am very skeptical about this interpretation of this effect. So the calculation that you are doing in order to compute Hawking effect or Uller effect has nothing to do with this virtual part being created. It's a completely different calculation. So this analogy, I don't see directly how it applies. It is a very tempting idea to use that analogy, but to me, it may be even more. I'm very skeptical.
But sorry, but when people measure the vacuum pressure, yeah, like you have two mirrors, and depending on the distance between two mirrors, you can measure the force that these two mirrors are apparently attracting, because not all particles can be between mirrors, because some particles have too big lengths, so they cannot be. So if the mirrors are closer, then they are attracting more, if I remember. Yeah. So and this effect is measured. Yeah. So
yes, it's called Casimir effect.
Yeah. And so I understand that this effect is based on creation particle antiparticle, or I'm completely wrong.
I mean, the way you derive this effect has nothing to do. I mean, if you do the calculation, what you do is you count the number of modes of the field.
Yeah.
Now, when you have a free field where there's no mirrors, the number of modes is infinite. You can have any frequency you want, right? You can have blue light, you can have red light, green light, whatever.
And then you have cutoff.
But when you introduce a mirror, then the mirror introduces boundary conditions, and then the number of modes between the mirrors is now limited. You can only have that frequency or another one, and these frequencies are quantized. So there is less modes available between the mirrors, more modes available outside of these mirrors, and the usual argument is that there is some pressure, quantum pressure imposed by each of the modes, and since there is less modes in between and more modes outside, then these modes on the outside pressure more the mirrors than those that are in between. That's the kind of hand-waving version of this effect. Yes, you can somehow make a case.
Hand-waving explanation is wrong?
No, it's not. I mean, you don't see this directly in the calculation, but somehow it reflects the speed of what you calculate. In the case of Hawking radiation, that hand-waving argument is not convincing to me. I mean, I don't see directly how this applies to this case. And for example, you have fluctuate. How do you explain the Unruh effect? Because it's related to Hawking radiation. How do you explain this? Well, spontaneous creation of a pair of particles takes place for a very small amount of time. Essentially, the idea is that if you make an observation of the vacuum for a very short time, then the time that you observe is finite. That means that the energy cannot be very specific because of the energy-time uncertainty relations. So if you don't make a measurement sufficiently long, that you cannot determine the energy very well. And since energy is not very well defined in this case, it's not necessarily zero. There could be a non-zero energy that you observe. And that non-zero energy is these fluctuations that you can observe if you make measurements of the vacuum for a finite time. These are the fluctuations. And then you can argue, okay, these processes can be expanded in diagrams, and the first diagrams look like a creation of pairs of particles. And they disappear immediately. However, the Unruh effect, it's not an effect that takes place for a short time. You can accelerate for very, very long, and you will keep seeing all these particles all the time. There may be some relation with the fluctuation of the vacuum, and sometimes people make this argument that this is related, but all I'm saying is that this analogy is very difficult to strictly carry out. You can hand wave, you can argue that maybe there's something there, that there's some relation between these. I spent some time trying to understand it better and I failed. I mean, I'm unsatisfied with this explanation. After all, there is a calculation you can make, and then I don't see directly how it relates to the hand-waving argument. However, I mean, this is interesting. Some of these effects are very somehow related, and it turns out that the whole structure of quantum field theory, these relativistic corrections, introduce a lot of interesting new ideas. So, there is another paper I'd like to tell you about, how to make this a bit more practical, if it's not too much to promise. So I have already argued that if you start to accelerate through the empty space, you will start to see particles. That is called the Unruh effect. Now, what happens if you take the empty cavity, 2 mirrors again, and accelerate the cavity that was initially empty? What happens to the inside of the cavity? Well, again, it's not, I mean, the consequence of the Unruh effect is that there will be some particles produced inside of the cavity. As you start to accelerate, you can produce you can change the state of the inside. That state is, you can compute that state. It turns out it has some interesting entanglement inside, very interesting structure. And then you can somehow engineer that state by choosing the way you accelerate your cavity. And we have shown that there are certain resonances in that state that you can use to enhance the number of particles that you produce in a cavity, because these numbers are very tiny, they are very, very small. The amount of particles that you produce is negligible usually, but if there is a resonance that you can find, and in particular in this case of the cavity, there are some resonances where you have to accelerate the cavity back and forth periodically, and with each cycle you will produce more and more and more particles. If you hit the numbers right, then you can in fact produce certain state inside of the cavity that is enhanced with every single cycle. And here we have plotted the amount of, well, to be more precise, the amount of entanglement that you create inside of the cavity, that you can quantify somehow. That's the vertical axis, that's a measure of entanglement inside of the cavity, as a function of the periods of acceleration and period of deacceleration. So we have considered a scheme where you accelerate the cavity for a finite time, then you let it move for a finite time with certain speed, then you go back, and the whole oscillation is characterized by 2 periods, the time of acceleration and time of free motion. And there are certain parameters that can hit for which it turns out that the amount of entanglement you produce is larger. And we have shown that with each cycle, you just multiply this amount of entanglement, and if you had an ideal cavity that does not have any leaks, which does not exist, but in a theoretical case, ideal case, you could increase the amount of entanglement without any limits. Obviously, for practical purposes, this doesn't work because there are no ideal cavities. Always there is some light leaking out. But in a perfect case, in a perfect world, you will be able to produce entanglement by just shaking your empty cavity, which is very practical. I mean, just take something, shake it, and then you get something inside. Now, it's not only that you can produce entanglement, but you can produce the very exact entanglement you want. And that's the question, what happens to an empty cavity? And we have also asked another question, what happens if the cavity initially was not empty? You had some state of the cavity inside, and then the question is, can you transform that state to something else by introducing certain motion of the cavity, by changing the way it moves? And it turns out that to some degree you can. To some degree you can transform an input state to some output state at your will. So to some degree you can perform certain simplified version of a quantum gate. That is the very basic concept of quantum computation. You can transform the input state into something else by just moving the cavity. Which is an interesting idea. I don't say it's very practical, but in principle this should work. In ideal case it should work. So in principle you could transform your quantum states, do what quantum gates normally do by just taking your system and shaking it.
Excuse me, how should we understand these numbers?
So usually in the effects like this, most papers in relativistic quantum information have this interesting property that nobody puts units on the axis. And the reason is that if you put units, it becomes laughable. It's just too funny to be even considered serious, because these amounts are really small. These effects are really tiny. So essentially it says that there is a very small amount of entanglement. In this case it's quantified by a certain method, it's called logarithmic negativity, and it's practically zero. So there is almost no entanglement produced in a single cycle. So that's why this is a theoretical effect, it's not practical. But again, if you repeat the cycle many times, you can increase it linearly. With each cycle, it just doubles and triples the amount of entanglement. So that was the idea, that you could actually find a resonance and then have this effect being observable. But the typical situation is that these numbers are really small. The effects are really practically negligible. So that's why I'm doing theoretical physics, not experimental. And the last idea that can use these effects I want to tell you about deals with a very elementary question in special relativity, namely the question of clocks, how they measure time. And you are very used to the case that, one of the basic properties of special relativity is that when a clock moves with a certain speed, with a fixed velocity, it will be slowed down. It will be slowed down due to the so-called time dilation. And all clocks slow down if they move. This is a universal effect. It applies to all types of clocks. For example, if I'm walking right now, my clock is slowed down, but my hair also grows slower, my heartbeat is slower, all the processes slow down by the same factor. It's called Lorentz factor, and that factor increases with velocity. Now, the question is what happens to clocks that accelerate. Now, and we ask this question because in literature this question has been asked many times, and there seems to be a default answer. The textbook answer to this question is yes, if the clocks accelerate, we know what's going to happen. And there is a certain formula, I'm going to discuss this formula. It's called the ideal clock formula. And what we kind of wrote about is challenging this idea. And we have shown that, in fact, this is not so obvious as most authors claim. This paper kind of got a little bit notoriety in press. And let me take a textbook description of this problem from the very respectable book on gravity by James Hartle. Here, he considers a situation where the clock moves, but not with a fixed speed, not with a constant velocity, but with velocity that changes in time. So we allow clocks that accelerate. What happens to accelerating clocks? Now, if the clock was moving with a constant velocity, then the rate of the moving clock is going to be affected by this extra Lorentz factor. So if d tau is clock measured by amount of time measured by the moving clock, and dt is the amount of time used by the resting clock, then the moving clock measures less time than the resting clock. This is the time dilation. And now the claim is that if a clock moves with a velocity that changes in time, what you need to do, you need to take an instantaneous velocity at a given time, compute the time dilation for that short moment of time, and then integrate it along the whole trajectory. And the result is this boxed formula that tells you that the moving clock along any trajectory will give you a lapse of time that is simply this integral that involves this extra Lorentz factor. Now, this is interesting because it shows that the amount of time measured by a moving clock only depends on its velocity and not acceleration. There is no acceleration in this formula, just velocity. And now if you think about this, if you take any clock you know, for example a pendulum clock, and you start to accelerate it, it's going to break. The pendulum will swing in a wrong rate and the clock will give you a wrong reading. If you take a more sophisticated clock, for example an atomic clock, this is the most precise clocks that you can think of. Atomic clocks is essentially a collection of lasers and atoms sitting on an optical table. Bunch of devices in the lab, right? What happens if you accelerate all that? If you shake it? It will just break down, right? It will just, all these lasers will fall on the floor, that's it. That will be the end of it. And in fact, all known clocks have that property. If you accelerate any clock, it will break at some point. Maybe not with acceleration g, but if I take an Apple Watch and accelerate with acceleration 100 g, I guarantee it's going to break. So what is really meant by saying that ideal clocks measure this integral that does not depend on the instantaneous velocity? So the idea is this. This is the formula that we are talking about. The idea is this. If you have a complicated trajectory, we approximate the trajectory with a bunch of segments that move with constant velocity, and then these velocities change at some points, and we kind of take the limit of very small segments, turn the function into, this bunch of segments into a small function, and assume that what happens in these points where the velocity changes does not matter. That these rapid accelerations do not play any role. And we kind of criticize this, because all real mechanisms really feel accelerations, and this formula for an ideal clock, what does it apply to? Which type of clock it applies to? Because notice that I first mentioned the time dilation effect that is completely universal. If I move with a constant velocity, every single clock will be affected the same way. Every single one. Doesn't matter whether it's my Apple Watch or pendulum clock or my heartbeat, they all are dilated by the same factor. It does not happen with accelerations. For accelerations, it's different for each clock. So the question is whether there exists any clock at all that can measure this. And in fact, this is a very important question, because the whole general theory of gravity, or relativity, is based on the assumption that there exist ideal clocks that measure this formula. Such as there exist ideal rulers that are not affected by strong gravitational fields. The whole construction of general relativity relies on the existence of clocks like this. So this important question, whether these particles can even exist. And let me go back to the textbook. The comment here says that it should be emphasized that this formula holds even for accelerating clocks when the velocity is dependent on time. Which is, I just criticize this view. And it goes, a famous test of this relation for an accelerating clock is described somewhere on another page. That particular test is really very important. And if you ask the question how to construct a clock that does not feel accelerations, you have to make this clock as simple as possible. It cannot have any structure. And it turns out that there are such interesting physical structures that are very simple, namely elementary particles. There is a particle called muon that decays very, very fast into an electron and a bunch of neutrinos. The decay rate is usually such that the average lifetime of a muon is of the order of microseconds. So if I put a muon here on the table, it will decay within a microsecond into an electron and something else. So in principle, we could take a bunch of muons, put them in a jar, and count them, how much of them are left, and that will give you an estimate of how much time has passed. The less muons in your jar, the more time has passed. So you could measure a rate of decay of the muon and ask whether that rate depends on velocity or acceleration. Now, it is known that muons do slow down their decays when they move with constant velocity, and there are many tests on that, even ones that you can perform on the tabletop experiments. And it turns out that yes, they are dilated by time dilation exactly the same way any other clocks are. But the question is, what happens if you accelerate a muon? And that test that the author was referring to involved an experiment with muons going in circles in accelerators very, very fast, so that centrifugal accelerations were really large. And it turned out that there was an experiment where the experienced centrifugal acceleration of the muon were of the order of 10 to 17 g, which is a lot. No structure will survive this acceleration. But muons do survive because they are just elementary particles. There is no structure inside. And they survived, and not only that, the observed decay rate did not seem to experience any acceleration. So the decay rate of a muon going like this was exactly the same as if the muon was going with the same velocity just on a straight line. So there was no effect of acceleration. And the author said, okay, so here's the ideal clock. The muon is an ideal clock. There you go. We have tested this up to 10 to 17 g, which is a lot. Now, we were kind of suspicious about this, and we have made a calculation what happens to a muon when you accelerate it and when you take into account all these funny effects I was discussing. And that's how I'm going to give you just the do I have a formula here? Let me see. Yeah. So it turns out that there is an effect of acceleration on the decay of a muon. I'm not going to go into details, and that decay rate depends on acceleration. Here it's denoted by alpha, proportional to the following factor. Now this particular function in physics plays a very important role because it's the so-called Bose-Einstein distribution, and it characterizes a state that has certain temperature. It has something to do with temperature. In particular, that temperature that is in this formula is somehow related to acceleration, and this formula characterizes a state of a fixed temperature that is proportional to proper acceleration of. I'm not going to go into very technical details, but that should ring a bell already, because I mentioned that another temperature that is proportional to acceleration is the one that is experienced by the Unruh effect, by the Unruh observer that accelerates. Now what happens here is that the accelerated muon in the vacuum, from its own point of view, is not in the vacuum anymore. The muon will experience particles around it, and the number of these particles is very small, it's negligibly small. But when accelerations become comparable to roughly 10 to 18, 19 g, the amount of these particles around start to play a relevant role. And it turns out that, indeed, from the point of view of the muon, there is a very, very small correction to its behavior due to acceleration, because the muon experiences all the particles around it due to Unruh effect, and these particles do affect the decay rate. So there is a very tiny correction that was not seen in that experiment, and we have computed what acceleration should be imposed on the muon so that it affects, so that it experiences these extra particles, and turns out that the number is really large, so it's very not practical, but in principle, the ideal clock formula for the muon is still an approximation. And the muon is not an ideal clock that is completely insensitive to accelerations. There is a tiny correction, and in principle, it should be taken into account. And for sufficiently large accelerations, the whole idea of measuring time with ideal clocks breaks down. And the conclusion is that this formula is only an approximation. We can estimate how much the approximation is in a given scenario, but that leads to very interesting problems, because in principle, it is going to be hard to define general theory of relativity in the highly non-inertial situations where clocks accelerate or experience very strong gravitational fields, and in that case the operational definition of time breaks down. So you can't even properly define what time is, because there is no universal units of time you could measure with a reference clock, because that will always depend on the system you're using. And these kind of questions pop up all the time when you try to combine relativity with quantum theory. These problems are very hard to get rid of, and we hope that eventually this will be solved. Yes, yeah.
So I'm just interested. So you said 10 to the 17 upward,
Yeah.
too small. How big is the number? Like more or less?
The question is so it's not an easy question, because for a circular motion, the acceleration is absolutely small. I mean, this goes beyond any observable experiments. Many orders of magnitude further than 10 to minus 10 to 19. However, the effect is completely different for linear accelerations. And but then again, the strict computation is difficult to carry out, and we had used some simplified models to compute the accelerations, and we got some numbers. But then to compare it with real experiments, it takes some extra work to do that. So we don't. I don't know the exact answer. What I know for certain is that there is some correction because of the Unruh effect, but the amount of that correction depends on the model you're using to simulate your muons. So I'm trying to kind of get away with that question because I don't know the right answer.
No, I know. Yeah, simplified form. I'm just. Can you hit me with the number? I'm just interested. Is it like 10 to the 30th?
So, for example, for the circular motions, when you consider circular motions, when you go to a circular motion quantum theory, what happens is that the circular orbits are quantized, and there are so-called Landau levels of those orbits that are allowed, and you need to take probably one of the lowest orbits, so one of the tiniest circles with really high velocities in order to see anything. And these orbits are of the order, the size of the orbit is probably smaller than the size of the atom. So this is a really very difficult thing to do. So you need to have a relativistic velocity with a circle that is really tiny to see that in a circular motion. So, but then you have other trajectories, you have linear trajectories, and for these trajectories, the effect is much stronger. So these problems with general relativity and defining it properly show up at scales that are really atomic.
Right. Yeah.
And so the question is how do you, yeah.
I was just wondering, had they run it to 10 to the 19th?
I was hoping for that.
They didn't have it.
I was hoping for that, and we were not really certain about this. I cannot give you a number of certainty. Sure. I know that there is some correction, and it increases of acceleration. Roughly speaking, this is the tendency, but for the linear motion, we had a simple model that said it's roughly the order of 10 to 21, I remember, G. But, so just a few orders more. But this was a simplified model with muons being treated like an toy model, not a strict QED calculation. So this is just a kind of first approach to it. Yeah, so essentially these are the questions and these are the problems that show up when you take the good old-fashioned quantum information theory and try to add some relativistic effects. Essentially all the questions start to be more difficult. Even asking a question, formulating a problem is a challenge sometimes, and this is what we are dealing with. This is not yet, again, relevant for practical purposes right now, but for those who are looking for quantum theory of gravity, which we don't know yet, and we will probably break down all the description that we had, this is some sort of landmark or hint what should be the properties of quantum theory of gravity in the semi-classical limit when the energies are not so large that you have Planck scale effects, but already start to show some relativistic corrections. And these will be the test bed for quantum gravity theories. For example, people ask the very important question, if you have a quantum theory of gravity, what happens near a black hole? Will it approximately produce Hawking radiation? Or will it approximately produce the Unruh effect when you accelerate in that theory? And that's the kind of test of the quantum theory of gravity, whether it makes any sense at all, because it has to, in some limit, recreate effects that you know from quantum field theory. So with that, I'd like to thank you for listening, and I'm open to questions. Thank you very much.
Thank you very much for very, let's say, breathtaking seminar with some discussions during the talk, but maybe you have more questions.
I have a question because the last number 5 for Anton Tillinger, it was for measuring the Bell inequalities in astronomical scales. So do you expect that the fidelity degradation that you mentioned here can play any role at all in this experiment? Because this is essentially what he measured, the fidelity.
Yes, so he was looking at, well, one of the experiments that he was awarded for, it was the quantum teleportation between two Canary Islands.
Yeah.
And the separation was of the order of, as far as I remember, 140 kilometers. The problem there is that I don't think he even performed the full quantum teleportation. He kind of did half of it, where the perfect measurement that should be made for the state to be teleported involves something that is called the Bell state measurement, and that is a very difficult thing to do. But there is a very simplified version of that experiment, where you only measure half of the Bell states. There are 4 of them, you only measure 2. And that will reduce the fidelity of teleportation by 50% right away. But if you post-select, if you only pick the situation where you did make measurements successfully, then you can teleport solve. So that's what he did. He did kind of this simplified version. So in this case, the degradation of entanglement due to this simplification and other factors is way beyond this tiny correction that we are talking about. So the answer is clearly no, and there is no observable effect to any quantum mechanical experiments performed nowadays. However, just let me comment to kind of support the idea of doing these things, that is not complete science fiction. So it is indeed difficult to observe these effects in quantum field theory directly, but there are ways to simulate these effects in other physical systems. For example, Hawking radiation is as tiny, if not smaller than the Unruh effect, and yet it has been observed experimentally in an analog system. So the idea is this. Instead of looking at the real black holes in the middle of the galaxy, you can create a system in the lab that is governed by the exactly same mathematical equations. It's a completely different system. It's a completely different physics, but the equations are the same.
You are talking about ADS-TFE?
No, I'm talking about BEC.
Okay.
Another acronym. It's the Bose-Einstein condensate. This is the experiments with clouds of atoms, roughly millions of atoms, cooled down to microkelvins, where they start to show superfluidity and other properties. They start to show something that is called Bose-Einstein condensation, where all these atoms end up in the same ground state and kind of share the same quantum state. They start to show quantum properties, and it turns out that the description of these objects, to some approximation, look very similar to the description of fields around black holes in certain scenarios, where instead of the speed of light, the constant c, you have the speed of sound in the BEC, which is much smaller. And that change from speed of light to the speed of sound makes a huge difference because all the proportionality constants become much larger. So you can start to see these effects in BECs that look like Hawking radiation of some sort from a black hole. And people have made these experiments and they claim that Hawking radiation has been already observed and other similar effects has been observed. For example, you mentioned the Casimir effect. There's a related effect called dynamical Casimir effect, which is a different one, which essentially is an effect where you take a mirror in empty space and accelerate the mirror in empty space, and a single accelerated mirror should start to shine light, should start to have a temperature. This is the same kind of related effect to the Unruh effect and Hawking radiation. That has been observed, and there was a Nature paper in 2014, I believe, where they have observed this dynamical Casimir effect in a simulated environment where instead of having a mirror in a vacuum, they had a superconducting circuit with some boundary conditions moving with acceleration, and they have observed a similar effect, a kind of analog effect. So you cannot directly observe these things, but you can observe analog effects in other systems. And this is an indirect confirmation that this is not a complete crap, but it has something to do with reality. Please, Tomasz.
How you know that math is the same?
What is the same?
How you know that the math is the same? That you may take the Bose condensate. I think that you have been talking about the second sound velocity and sound velocity, but nevertheless, how you can like prove or build an intuition that you have the same math when you take the Bose condensate and you have this problem. I mean, I am completely not against doing such theories because it is extremely interesting and challenging, but how you can get intuitions that math in both cases is the same.
So first of all, I'm in an excellent position because it's not my job to do that, but it's the job of the guy who did the experiment. The guy is called Jeff Steinhauer. The amazing thing about these experiments is that there are two Nature papers that he wrote, where he made the experiments and the papers are single authored, which is unusual. So he apparently he did it himself. And the idea is that, I mean, we do know a lot about Bose-Einstein condensates. They are known, they have been around since 1995, where the first Nobel Prize was awarded, I think, for the manipulation of Bose-Einstein condensates. And since then, we have like 25 years to develop the theory. the theory is well understood, and there are people who make very, very subtle experiments and make precise measurements that fit the theory, where you can manipulate these condensates, you can drop them, you can interfere them, you can make many things, you can excite them and watch excitations. And the theory, the approximate theory of these condensates is very well working. And you can essentially...
Right. In the case of Bose-Einstein condensate, but in the case of say, quantum gravity or anything approaching quantum gravity.
Yes,
I mean to compare two mass.
Yes, so on one hand we have a theory of Bose-Einstein condensates. On the other hand, we do not have quantum gravity, and everything I've been talking about today has nothing to do with quantum gravity. What we are doing is that we are taking a regular quantum field theory and take the quantum field theory to a non-inertial frame of reference. You just observe the quantum field theory from the uniformly accelerated relativistic frame of reference. So we are not modifying quantum field theory. We are just assuming that you can take any frame of reference you want. In particular, you can take not only inertial but non-inertial frame of reference and see what are the consequences. And it could be very well possible that there is no other effect. These effects do not happen at all. You make an experiment, they are not there. But the consequence of that would be even worse, because you would need to modify the quantum field theory, because the one that we know right now is good to be used in any frame of reference you want. It's covariant. Relativistic covariant, you can use any observer you want. If it turns out that there is no other effect, no Hawking radiation, that means that the quantum field theory that we know is wrong. It's only approximation, and we have to modify it. That would be an even bigger disaster than having to deal with these effects. So.
Okay. I think that we are in the point that I would really like to understand. So you take the classical or you take the quantum theory, and now you'd like to make this quantum theory in not inertial moving frame. So
yes.
So to do the quantum theory in non-inertial moving frame, this is just math, or you need any physics? I'm completely not an expert, but
Right. So special relativity tells you what happens if you move at a constant velocity. You can change the frame of reference from one that is rest to one that's moving, and mathematically speaking, all you have to do is change coordinates in a certain way, right? This is called Lorentz transformation. And this has been tested well, and the property of quantum field theory is that it is the same in all inertial frames of reference. The equations are exactly the same. So when you change the coordinates according to Lorentz transformation, the equations are exactly the same. Now, if you take special relativity, the classical theory, and consider accelerated frames of reference, which you can also do, which will approximate the situation. I mean, they will kind of create an approximation that is similar to physics around black holes, so that physics of classical observers next to black holes is similar to ones that accelerate. There is also a certain transformation of coordinates that corresponds to change of frame of reference. So you can start with the initial frame and then change coordinates to one that correspond to accelerating observer. That other transformation is called Rindel transformation. Another set of formulas for that. And essentially you change coordinates, that's all. And when you take a quantum field and transform it not to another Lorentz frame, but to a Rindel frame, so make it accelerate, the equations change. Which means that physics, quantum field theory in accelerated frames is different than quantum field theory in inertial frames.
And the second transformation, Rindel
transformation.
It is like observe that it works, or this is like a proposition that this is a correct transformation for.
No, you can derive it, and in fact, all general relativity, and I mean, this is a source of. This is how you derive general relativity. Really. So the idea of general relativity is that the equations in gravitational fields should be indistinguishable, approximately, from equations in non-inertial frames of reference. The example I gave before, if we turn off gravity in this room and just start to accelerate, physics should be the same. And that's how you can kind of link together gravity with acceleration, and the whole classical theory is based on this equality of acceleration and gravity. So the Rindel transformation I was mentioning is a well understood concept from the 50s. it's a classical relativity concept, and in classical theory, it's well understood that this should be the right transformation. The same way that Lorentz transformation corresponds to moving with constant velocity. Now, when it comes to quantum field theory, the idea is that it should be relativistic. The whole idea of quantum field theory that the underlying mass should be the same, should be right to be used in all frames of reference you want. Not only inertial, but also non-inertial. And the problem here is that nobody has tested this because all these effects become relevant for really high accelerations, like the Unruh effect. So this has not been tested. But again, the paradigm that we are using right now is that quantum field theory is as good as in any frame of reference you want, including the one that are accelerated. So the theory is unambiguous. We don't have experiments yet because they're difficult to carry out. We only have analog experiments. So this is kind of a way in between. So in a way, Hawking could not celebrate his effect because it was just a theory. However, again, it could turn out that the theory is wrong. And that doesn't happen. There is no Hawking radiation. But that would mean that the quantum field theory as we know it would have to be changed. And quantum field theory is the best theory we have so far. It's the most precise theory of reality we've ever had. So, certain calculations in quantum field theory involve correctness and agree with experiments up to 10 or more digits after a comma. So it's the most precise theory we've ever had, and saying that it's wrong would be a kind of a huge earthquake. So that's all I can say. That the theory is meant to be used in any coordinates. It should be used. It could also be used in non-inertial frames of reference. There is nothing wrong with that, and in fact, people have been doing that for a long time, roughly since 70s, since the works by Davies and Fulling and Hawking and Unruh. This is a kind of topic that seems to be well understood, and also people believe that this approach should be some approximation to some unknown quantum gravity. But again, it's a classical field. The quantum field theory concept is nothing non-orthodox.
We have another questions.
Hello. So I have a two-part question. One of them, as you said, when the particle is being accelerated, it sees other particles around it.
Yeah.
But it experiences like that. Is there a possibility for that particle to collapse with one of those particles around it? And the second part is, which one of your theories do you expect to be tested experimentally first? Thank you.
So yes, one signature of that interaction with other particles is the way in which the decay rate of a muon is affected. Because muon interacts with other particles of the state around it. And it's typically assumed that the state around it is the vacuum state. You have a single muon in the vacuum and it decays at a certain rate. If you put it inside of the thermal state, if some particles around, then these particles will affect the decay rate due to interactions. So in a way, the effect of the acceleration on the decay rate can be viewed as the consequence of interaction of your muon with these other particles that it experiences. So this is a sort of interaction that, I don't know if this is what you were asking about.
Yes, that was exactly what I'm asking for. So for example, a beam of light, for example, it is not accelerated. I apologize because my field is not a mathematician or I'm not a physicist, but so a beam of light should experience the most resistance when it moves toward the empty space.
In fact, the theory says that in principle all sorts of particles will be produced when you accelerate. When you accelerate, all fields will be excited. You'll see electrons, muons, electrons, all types of particles will be produced due to acceleration. However, most of these particles will be very few. In all practical purposes, the massive particles will be the least observable ones. The ones that you should expect to be observed first are photons, particles without mass. Therefore, the black hole, the evaporation of black holes should mostly be implemented with photons. So mostly photons will be emitted from the black hole. Also, there should be tiny amounts of electrons and other particles, but these are very negligible numbers. So if ever we will see anything there, I would expect that there will be photons first. That will be produced, first of all, massless particles like photons. And this actually we have asked this very question in a certain. We had a project about this particular question. What is the probability of finding a particle that has a mass in the inner effect, and that mass destroys the effect even more? So the most probable answer would be that you should expect observing photons.
We have another question.
Let's say sorry that I was delayed here. It is great talk, really great talk.
Thank you.
Because I was delayed, I couldn't catch all the sense, of course, because there is a gap. The sense is kind of, let's say, central wording. This is what I wanted to say to you. This is kind of hypothesis which I would like to, so that you will accept or refund using the quantum computing or quantum physics, right? And I will start with the following citation. I will read it from the translator, just showing, demonstrating that the sense is not necessarily is there. Grandma was sowing poppy seeds. She didn't know how, and the grandpa knew how. I'm sorry. He didn't say, and he was yes. I'm sorry. This is not well done. I will say it first in English, in proper version, which I think that there is a sense. Grandma was sowing poppy seeds. She didn't know how, and grandpa knew, but he didn't say, and it was as follows.
Okay, so
in Polish it will be siała baba mak. Nie wiedziała jak, a dziad wiedział, nie powiedział, a to było tak. So I will switch again to English and will try to explain it. It will be the complex. It may be recognized as a complex question, but it's a very simple question. The question which we try to answer together with my supervisor, Professor Bobrowski, from the nearby Institute of Maciej Nałęcz Institute of Biocybernetics. And we try to catch a sense in the book called Evolution, which was wrote not by us, but by Gaude Mater Natura, our mother nature. There is some sense hidden in this book, and what we try to do, being modest as engineers, being on the lowest level, trying to say at the beginning that we do know nothing. We try to read something which is between lines. How I try to read between your words, which I will return in the end. Okay? And then maybe I will just try to refer to two other things, which will be more and more mathematical. Okay? I'm sorry.
Ale szanowny panie, szanuj pan ludzi, no gadasz pan 10 minut i popisujesz się pan zamiast powiedzieć coś konkretnego, no.
So this is what I try to say as a concrete. If you want to stop at this moment, I will stop this and I will come to you and ask after that. That's the decision. Please vote. Evolution is about voting.
I'm here, so I'm happy to discuss afterwards as well. So.
Okay. So, should I continue or not?
Yes.
Okay. So what we are doing in practice, just trying to read between lines in this evolution book, we try to disentangle. There was a word entanglement, right, which you use in your great presentation. So, using the equation discussion of the equation which is inégalité plus fraternité égale liberté, where there is some sense. This is about producing the sense and logic on the way as a derivative, just, you know, performing equation discussion of that. And then using the proof by denial or by defending. This is mathematical, let's say, the simple thing which we can do. And also using the mechanic of the, let's say, using this proof by contradiction, and also, let's say, strategy to the students, which is just, let's say, just equalizing to the higher value, and starting from the assumption that we do not nothing, and then that the process of producing sense is trying to go from the lowest level by learning from the master. This is equalizing from to the master, and then finally coming to the place where people as students are coming to the exam, which is just trying to come to the place of truth, and then the master will equalize you to the bottom, right? So this is the sigmoid, right? In other words, this is the spiral which you showed. This is the spiral from the place where we equalized at the beginning. This is scientific process to the floor. Then we are going to equalize you during the learning process to the place of your master. And finally, at the exam, we are going again when you will be equalized to a lower grade, just because of the rules. And of course, when we go to the word, we will get wired, so we'll try to go up to the stairs, right? Like other citation is Adam Mickiewicz says, młodości nad poziomy wylatuj. This is the end of my question. Question is how, using the words which you heard, right, and which refers, because the first citation is about going from the, let's say, place of logic, which grandma says, dziad miał sens, tak? I dziad wiedział, jak posiać mak. I też w maku był pewien sens, który biologia zrobiła, a baba tego nie widziała, a dziad mógł wyprodukować ten sens. I to jest pytanie. That's my question. Thank you very much.
Okay, I mean, the question is not very precise. I mean, I don't think I understood it fully. But one comment I can make, perhaps, that could be useful, is that let me quote, I guess, Feynman again. Feynman says that in order to communicate, you cannot be precise. That the necessary condition for communication is lack of precision. So, the learning, I mean, for example, I'm giving a seminar today. It was not very precise. I was just skipping some technical details, and that means I was not very precise. I was, well, to be blunt, I was just lying to some degree, and that was necessary for me to communicate anything. Once we have established certain understanding, I can go into more details and say that it's not exactly as I explained, and there's more layers and more layers. So I guess the process of sharing knowledge is always like this, that you have to lie a little bit, just like lie to your children. When you raise the children, you lie all the time. You say that it's going to go to school, and the teacher will say everything that is correct, and she will be always right, and she's good, and the policeman will catch bad thieves, and they are good, they are bad. These things are kind of black and white, and they are obvious lies, because this is not the way things are, right? But you cannot start right away with quantum field theory when you raise a child, right? You have to go make it in steps. That's one reason to lie, because you want to establish communication. The second reason is that we don't know reality very well to know ultimate laws of physics. We only know some approximations. So even if I wanted to be very precise and tell all the truth, then I can't, because I don't know what the truth is. I don't know quantum gravity. I have some approximations on it. So again, this is always, the process of learning will always involve lack of precision, which is essentially like.
So maybe I will ask you the last question. So I will refer to the title of the talk. So in BC systems, is there any structure which corresponds to black holes? Something like this.
In BECs?
Yeah.
Well, not really. It's a completely different system. So it's interesting that you have a completely different physics. You have just cold gas, and somehow it's you can characterize excitations of the field of those particles And the equation of excitation is exactly this, can sometimes look like the quantum field theory in the proximity of black holes. So physics is completely different. They have nothing to do with each other, and yet mathematics is the same.
Okay.
And there was this famous quote again that the same equations have the same solutions. So if you believe that the equations are the same, but it's more difficult to access this physical system because, I mean, it's very far away, you cannot make an experiment with it. So you take another system that has the same equations, the solutions will be the same, so observations should be the same, and that's how you infer that if you get this kind of emulation of Hawking radiation here, you should expect a similar effect far away in the middle of the galaxy. But physics is completely different.
And the effects you were talking, Unruh effect and Hawking radiation, do they influence somehow the prediction about the fate of black holes?
I mean, that's the belief that that eventually evaporating black hole will decrease its size, and eventually there will be nothing left. The problem here is that, first of all, the theory of radiation of black holes is, again, a bunch of approximations. And one approximation that is crucial here is that when you produce those particles that radiate out of the black hole, those particles do not affect the gravitational field around. That's an approximation, because the black hole is very strong, the emitted stream of particles is very weak, it has no effect on the gravity. If you make that approximation, that means that the black hole will evaporate all the time without changing the mass, which is kind of clearly wrong because the energy must come from somewhere. So we see that somehow these approximations only give you certain answers, but they are clearly wrong when it comes to the fate of the black hole. So then you have to correct your approximation and say somehow that radiation will carry away energy, and that energy must come from somewhere, so clearly it goes from the black hole, so the black hole must shrink due to conservation of energy of some sort. And this is hand-waving again. There is no strict model of that process because we don't have quantum gravity again. We need quantum gravity to characterize this precisely. So this is just hand-waving. There must be something that causes the black hole to shrink. And there are some hand-waving arguments about upstream of energy and so on and so forth. So we expect that eventually the black hole will shrink. And the theory says that initially the shrinking will be very slow, but as the black hole turns smaller and smaller, the very final stages of the evaporation will be crucial, and then the evaporation will enhance. So small black holes evaporate very quick, and big black holes evaporate very slowly. So the final stage will, according to the theory, will look like an explosion. And in fact, the first paper that by Hawking in Nature, this kind of short announcements of the result, was called Black Hole Explosions, ? That was the title of the paper. And yet, we have no idea what happens at the very final stage, at the very end. And there are some speculations about what happens. One of the speculations is that there will be nothing left of the black hole. It will go all in radiation. The other speculation is that there will be something left. This is called a remnant. But again, to answer these questions, we need quantum theory of gravity, which we don't have. And essentially, this is one of the biggest problems in gravity theory for the past 100 years. We have celebrated 100 years of gravity, Einstein and gravity, but equally well we could celebrate 100 years of not inventing quantum gravity. This would be more appropriate, maybe.
Thank you very much, and both for your very interesting talk and for your very exhaustive answer. And okay, I think I've understood some things. Maybe the audience also. So once more, thank you for accepting your invitation.